This is part 4 of lecture 4.1, Relations. In this video, we will define reflexive, symmetric, antisymmetric, and transitive relations and give examples of proofs involving these concepts. Let A be a non-empty set and let R be a relation on A. R is said to be reflexive on A if and only if for any element X in A, X is related to itself under R. R is symmetric if and only if for any elements X and Y in A, if X is related to Y, then Y is related to X. R is antisymmetric if and only if for any elements X and Y in A, if X is related to Y and Y is related to X, then X equals Y. R is transitive if and only if for any elements X, Y, and Z in A, if X is related to Y and Y is related to Z, then X is related to Z. For any set A, the identity relation on A is reflexive on A, since for any element X in A, X is equal to itself. It is symmetric since for any elements X and Y in A, X equals Y implies that Y equals X. It is antisymmetric since for any elements X and Y in A, X equals Y and Y equals X clearly implies that X equals Y. It is transitive since for any elements X, Y, and Z, X equals Y and Y equals Z implies that X equals Z. The relation greater than on the set of real numbers is not reflexive on R. That is, it is not the case that for every real number X, X is greater than itself. That is, for some real number X, X is not greater than itself. We know that the statement X is greater than X is false for every real number Y by the trichotomy axiom. In particular, 1 is a real number, but 1 is not greater than 1. So the relation greater than is not reflexive on R. It is also not symmetric on R. That is, it is not the case that for every real numbers X and Y, if X is greater than Y, then Y is greater than X. That is, for some real numbers X and Y, X is greater than Y, but Y is not greater than X. We know by the trichotomy axiom that for any X and Y, if X is greater than Y, then Y cannot be greater than X. In particular, 0 and 1 are real numbers with 1 greater than 0, but 0 is not greater than 1. So the relation greater than is not symmetric. The relation greater than is antisymmetric. This is because for any real numbers X and Y, the statement X is greater than Y and Y is greater than X is always false. Hence, the statement if X is greater than Y and Y is greater than X, then X is equal to Y is vacuously true. So the relation greater than is antisymmetric. It is transitive. That is, for any real numbers X, Y, and Z, X is greater than Y and Y is greater than Z implies that X is greater than Z. The relation greater than or equal to on the set of real numbers is reflexive on R, since for any real number X, X is greater than or equal to X. It is not symmetric, that is, there exist real numbers X and Y such that X is greater than or equal to Y, but Y is not greater than or equal to X. In particular, 1 is greater than or equal to 0, but 0 is not greater than or equal to 1. It is antisymmetric since for any real numbers X and Y, if X is greater than or equal to Y and Y is greater than or equal to X, then X is equal to Y. It is transitive since for any real numbers x, y, and z, if x is greater than or equal to y and y is greater than or equal to z, then x is greater than or equal to z. Consider the relation on the set of non-zero integers consisting of all ordered pairs AB such that A divides B. This relation is reflexive on R. Indeed, let A be a non-zero integer. Then A is equal to A times 1, so A divides itself. It is not symmetric. That is, there exist non-zero integers A and B such that A divides B, but B does not divide A. For instance, 1 and 2 are non-zero integers and 1 divides 2, but 2 does not divide 1. It is not antisymmetric. That is, it is not the case that for any non-zero integers A and B, if A divides B and B divides A, then A is equal to B. Equivalently, there exist non-zero integers A and B such that A divides B and B divides A, but A is not equal to B. For example, the integers 1 and -1 divide each other, but 1 is not equal to -1. It is transitive, that is, for any non-zero integers A, B, and C, if A divides B and B divides C, then A divides C. This follows from an earlier exercise. Let M be a fixed positive integer. Define the relation congruence modulo M on the set of integers as follows. For any integers A and B, A is congruent to B modulo M if and only if M divides A minus B. The relation congruence modulo M is reflexive on the set of integers. Indeed, let A be an arbitrary integer. Then A minus A equals 0, which is equal to 0 times M. So M divides A minus A. Therefore, A is congruent to itself modulo M. The relation congruence modulo M is symmetric. Indeed, let A and B be arbitrary integers. Assume that A is congruent to B modulo M. Then M divides A minus B. Now, B minus A is equal to -1 times A minus B. It follows that M also divides B minus A. Therefore, B is congruent to A modulo M. The relation congruence modulo M is not antisymmetric. That is, there exist integers A and B such that A is congruent to B modulo M, B is congruent to A modulo M, but A is not equal to B. As a counterexample, consider the numbers 0 and M. Clearly, 0 and M are integers with M divisible by M, and -M divisible by M. Thus, M divides both M minus 0 and 0 minus M. So M is congruent to 0 modulo M, and 0 is congruent to M modulo M. However, M is not equal to 0 since M is a positive integer. The relation congruence modulo M is transitive. Indeed, let A, B, and C be arbitrary integers. Assume that A is congruent to B modulo M and B is congruent to C modulo M. Then M divides both A minus B and B minus C. Hence, M divides the sum A minus B plus B minus C. Therefore, M divides A minus C. It follows that A is congruent to C modulo M. Let A be a set and let R be a relation on A. then R is reflexive on A if and only if the identity relation on A is a subset of R. This is equivalent to the statement for any element small a in the set A is related to itself under R, if and only if for any elements X and Y in A, if X, Y is an element of the identity relation on A, then X, Y is an element of R. We begin by proving the forward implication. Assume that R is reflexive on A. Let X and Y be arbitrary elements in A. Assume that the ordered pair XY is an element of the identity relation on A. Then Y is equal to X, so the ordered pair XY is equal to the ordered pair XX. Since R is reflexive on A, XX is an element of R. Equivalently, XY is an element of R. Thus, the identity relation on A is a subset of R. For the converse, assume that the identity relation on A is a subset of R. Let small a be an arbitrary element of the set A. Then the ordered pair AA is an element of the identity relation on A. So AA is an element of R, that is, A is related to itself under R. Thus, R is reflexive on A. Consider the following claim. If the domain of R is equal to A, and if R is both symmetric and transitive on A, then R is reflexive on A. We write this in symbols as the conjunction of the domain of R equals A, and R is symmetric and R is transitive, implies that for any small a in capital A is related to itself under R. To prove this, assume that the domain of R equals A and that R is symmetric and transitive. Let small a be an element of the set A. We need to show that A is related to itself under R. Since the domain of R equals A, it follows that small a is an element of the domain of R. Hence, there exists an element B of A such that A is related to B. Since R is symmetric, B is related to A. So both A is related to B and B is related to A. Since R is transitive, A is related to A. Therefore, R is reflexive on the set A. You have come to the end of part 4 of lecture 4.1. Before you proceed to lecture 4.2, you are strongly encouraged to do the exercises at the end of these slides. Thank you for your attention.